Hello guys, good morning. Um, right, let's get started. We're gonna do ideal gases today. If you've done chemistry, this would be familiar. Okay, so the notes and stuff I've already uploaded on Google Classroom. You can just download it from there. Okay, so there's going to be a bunch of equations that you need to be familiar with. We'll talk about that when we get to it. Make my pointer bigger. And then you also need to know the four assumptions of an ideal gas. Is it four? Is it five? I think it's four. Four assumptions of ideal gases. And you need to know how to derive the equation of state of the ideal gas using the a series of steps, which I will explain in a bit. And then later you will see that the kinetic energy of a molecule is proportional to the temperature of a substance, which gives you an idea as to what temperature actually means. Because you've always been told that well, I mean, okay, you haven't been told this, but you don't really have how do you associate temperature with a physical property of a substance, right? What exactly is temperature? So it turns out for an ideal gas, specifically for an ideal gas, the temperature of an ideal gas depends only on the kinetic energy of the molecule. So we're gonna have to show that later. Yep, so essentially that's it. So what is the kinetic theory of gases? Excuse me. So the kinetic theory of gases tells you that the gases are made of particles in a random rapid motion with a distribution of speeds in different directions. So basically made of particles, they fly in random directions at some random speed, well, at some constant speed. And but these particles have a random distribution of speeds. So this particle could be faster than this one. It kind of follows like a normal distribution curve and go in random directions. That's essentially what the kinetic theory of gases is. So you can, it's actually here. You don't have to write it down because it's already here. Second line. Okay, so in order for us to make some approximations, well, some calculations, we have to make certain approximations, aka assumptions. So these are the assumptions we have to make for a gas to be ideal, right? Since physics is all about, I mean, if you're trying to predict something with absolute precision, it's very difficult because you have a lot of different factors like air resistance and whatnot. So usually when it comes to simplifying calculations, you ignore certain parts of the model that may be insignificant, like air resistance. You can just ignore that if it doesn't really contribute much to the end result, which makes everything easier. So for gases, you can make these assumptions to make the calculations easier. So the first one is the size of the particles are insignificant compared to the size of the container. Second one is the particles are in constant, random, and rapid motion. Right, they're moving with some constant speed and random direction. The collisions between the particles and the walls of the container are perfectly elastic, so no energy is lost when they collide. And then except during collisions, the forces of gravity and the forces of particles exert on one another are negligible. So the last sentence basically means you can ignore the weight of the particles, because the weight of the particles are insignificant compared to the reaction force from the walls of the container. So we can just ignore them. So you're essentially assuming that the ideal gas particles are weightless, they are perfectly elastic, they move at some constant speed in some random direction. And by random, that means it's completely random. There's no preference for a particular direction. And that the particles are basically point particles. They're so small that we can just ignore the size, the volume of the particles. So these four, you want to write that down in your list over here. So just leave it here for a bit, and you can write them down, or maybe copy paste the screen or something. So I'll give you a moment. Okay, moving on. The equation of state of the ideal gas. So if you've done a bit of chemistry, you would have seen this before. PV equals nRT. So P here refers to the pressure of the gas. V refers to the volume of the gas. N is the number of moles of the gas. So number of moles is just another way of saying how many particles there are. We'll talk about that in a bit. R is the molar gas constant, which has a value of 8.31. Oh, sorry, someone's calling me. Sorry about that. So R is the molar gas constant. And it has a value of 8.31. N is the number of moles. So 1 mole has 6.02 times 10 to the power of 23 particles. So if I say I have 2 moles, that means I have 2 times this amount of particles. T here is the absolute temperature of the particle. Absolute temperature. That means temperature in kelvins. Hello, Elise. Good morning. Good morning. Okay, P is the pressure, V is volume. So how do you get this equation in the first place? There are actually 2 ways of doing that. The first way is you do it experimentally by using the 3 gas laws. So you might have done this in IGCSE, I think. The Avogadro's law, Boyle's law, and Charles' law. So Avogadro's law tells you that the volume of a gas depends on the number of moles of the gas. So the more particles you have in a given space, the volume would increase. And this is assuming that your pressure is constant. This is assuming your pressure and temperature is constant. Then V will be proportional to the number of moles. Boyle's law. What does Boyle's law tell you again? I can't remember exactly which one is which. This is not in your syllabus anyways, but I think one of them is the pressure is inversely proportional to the volume. And then the other one is the temperature is proportional to the volume. This one is assuming that temperature and the number of moles is constant. And this one is assuming that pressure and number of moles is constant. Yep. I forgot whether this one is this one or this one is this one, or is it the other way around? I could be mistaken, but the point is these are the gas laws. And you can check that using an experiment by keeping these values constant, and you see that these would be proportional or inversely proportional. So if you want to combine all these things together, noting that these are the variables that are constant, you would actually end up with this equation right here. Okay, so that is one way of doing that, one way of deriving this equation. The other way is the one that is relevant to our syllabus, which is to derive it using the power of maths, which I'll show you in a bit. Okay, so next up, let's talk about the Avogadro's constant. So the Avogadro's constant, the definition for this is actually the number of atoms in 12 grams of carbon-12. Carbon-12 is an isotope of carbon. Right, so 12 grams of carbon-12 has this many atoms in it. So that's the Avogadro's constant, which is given by this symbol here, and with a capital A. The symbol, the unit is per unit mole. Okay, so just write it down, because that's something that they could potentially ask you in the exam. I shall give you a moment. Okay, right, moving on. So what exactly is 1 mole? 1 mole is the amount of substance containing the same number of particles as 12 grams of carbon-12. In other words, the amount of substance that contains 6.02 times 10 to the power of 23 particles. Okay, it's the same, so the number of particles in 12 grams of carbon-12 is the Avogadro number, which is 6.02 times 10 to the power of 23. If you've done chemistry, this is the same thing. Though I think the definition in chemistry is slightly different. I'm not exactly sure how it's different, but I remember someone mentioning to me that it's worded slightly differently in chemistry. But in any case, this is the one that they expect you to write in physics. So it is what it is. Okay, moving on. So what exactly is an ideal gas? So obviously we know the ideal gases, an ideal gas would obey the 4 ideal gas assumptions. But a more concise definition of the ideal gas is this. An ideal gas obeys the law PV equals to some constant times T at all values of P, V, and T. So the constant here refers to the number of moles times R. Okay, so this is the kind of, this is what you want to write in the exam if they ask you for the definition of an ideal gas. Obeys PV equals this at all values of P, V, and T. Okay, very important definition. Please commit it to memory. Oh. Okay. All right, all good. If you can't write this down quickly enough, you can always take a screenshot, or you can refer to the material that I've uploaded on Google Classroom. It's all there. Moving on. Excuse me. So next up, we have the microscopic derivation of the equation of state of the ideal gas. So we're going to try to derive PV equals nRT using the power of maths. So suppose we have a container with a cross-sectional area A1 and A2. We're going to say that A1 and A2 are the same because this is, let's say, a cube. And then we have a particle with some mass m moving along in the x direction with some speed vx. Okay, and the length of the container is given as L. Right, so that's the setup of the thought experiment that we're going to try to use to derive the equation of state of the ideal gas. Okay, so Now, if I can direct your attention to page 3 on your notes. Right, so we're gonna go through each step slowly. So the first one is find the time interval delta t between each successive collision with one of the phases A1 or A2. Okay, so we have this particle moving with some speed Vx, and it's going to collide with A1 and bounce off because it is perfectly elastic, one of the assumptions of the ideal gas, remember? So successive collision here means it hits this, bounces off, and comes back and hits it again. So how much time has elapsed between each successive collision? So hits, flies off, flies back, hits it again. How much time has passed? So remember, one of the assumptions of the ideal gas is that they're moving with constant speed, which means there is no acceleration, which means the acceleration is always zero, which means constant acceleration, which means we can use the kinematics equation, right? So let's use a kinematics equation to find the time taken. Let's use S equals ut plus half at squared. We know a is 0, so this poof disappears. And we're trying to find t, right? So delta t is equals to S over u. S is going to be the displacement. So that's, well, S is going to be the distance traveled, essentially. So that's going to be here and then here. So that's 2L, okay? 2L. 2L. Technically, what's happening here is S is referring to the displacement. And if you go from here to here, let's say this point is S equals 0. This point is S equals to negative L. Okay, let's say going to the left is negative. So how should I explain this? Okay, you know what? Just think of this as the total distance traveled. All right, total distance traveled. So u here is going to be the speed, which is going to be Vx. And there you go. That is the total time taken. Done. Should I explain it this way? Yeah, I think that's fine. Oh, German MP, thanks for the follow. Welcome. Right. You know what? Maybe I'll try to explain it in terms of the displacement, because technically S here refers to the displacement rather than the total distance, right? So let's try to be consistent. Okay, so if you go from here to here, let's say this guy is S equals 0, this guy is S equals to negative L. So going from here to here means your total time taken would be negative L and then negative Vx, because V here refers to the speed. So if you are moving in the opposite direction, you have to put a negative, which means you would get L over Vx. Okay, so this is the time taken going from this point to this point. Now, if you go from this point to this point, let's call that delta t2. You would be going in the positive L direction, and you would have a speed that's a positive Vx. So you would have L over Vx. So the total time taken is going to be this guy plus this guy, which is why you get this guy in the first place. Okay, hopefully that makes a bit more sense. Moving on to the next question. The next step, sorry. Find the change in momentum between each successive collision with one of the phases. So, how do I find the change in momentum? remember the change in any value is always the final value minus the initial value. So what is the definition of momentum again? Momentum is the product of mass times the velocity, not the speed, the velocity. Okay, be very careful. This is a vector, so the direction matters. So we're gonna put that in here. So v minus mu, factorize m, v minus u. So what is v? V is the final velocity. All right. So initially, okay, how should I explain this? So initially, your particles coming in like this, right? With some velocity vx, and then after that it bounces off with some velocity negative vx, because remember the vx here refers to the speed, not the velocity. So we have to put a negative to show that it is going in the other direction. So my final speed is going to be negative vx. My initial speed is minus vx. So we end up with negative 2 mvx. There we go. So that is our change in momentum. Typically, in the context of A-levels, whenever they ask you for the change of something, they are actually referring to the magnitude of the change, which means you don't really care about the negative sign. So let me just put that here. The magnitude of the change is just 2 mvx. Okay. Part C. Find the average force being exerted on one of the faces of the container. So how do I find the average force? You have to use Newton's second law. So what is Newton's second law? Newton's second law tells you that the force is the rate of change of momentum. Oh, I just realized something. I don't think we had our class yesterday. We should be having a class yesterday at 3 to 5. I completely forgot about that. Why did you guys not remind me? Okay, we have to replace that somehow. Let's do 1 hour on 1 hour next Monday. Next Monday, yeah. I think we can do 1 hour next Monday. We'll do after the chemistry class. Okay, yep. So next week we'll do Monday, Tuesday, Wednesday, Friday. Yep. Okay, anyway, coming back to this. Change in momentum. Well, we know what that is because we worked it out earlier, is 2 mvx. And then the time taken is 2L over Vx, right? So simplifying this guy, we are going to get m bracket Vx squared over L. And that is the average force exerted on one of the faces. Average because you're dividing it over some period of time. And that period of time is not the collision time. It is the time taken between successive collisions. So that's why it's the average force rather than the instantaneous force at that particular point in time. Okay, part D. Find the average pressure being exerted by one particle on one of the faces of the container. Then, considering the container is a cube, we can say that the cross-sectional area times the length of the cube is the volume of the cube, right? Area times length equals volume. Okay, so how do I find the pressure? The average pressure is going to be by the definition of pressure, is going to be force over area, right? Force per unit area. So we know what the average force is because we worked that out earlier. Is mvx squared over L, and then we're gonna have A times L. And as you can see, the areas are the same because it's a cube, so A times L must be the volume. So we get mvx squared over the volume of the cube. There we go. Now, part E. Now consider that having n particles traveling in the x direction with speeds v1x, v2x until v and x. So basically you have n particles. They're traveling in the x direction. They're all traveling horizontally, and each of them have speeds v1x, v2x, and so on, respectively. So each particle have their own associated random speed, but they're all moving with some constant speed. Okay? Again, this is one of the assumptions of an ideal gas. They are all moving with some constant random motion. Write an expression showing the total pressure being exerted on the face of the container by these particles. Assume the particles have some have the same mass. So how do I find the total pressure? So the total pressure, also written as Pn in this case, is going to be the sum of all the pressures of all the particles, right? So you have to take, the pressure due to particle 1 plus the pressure due to particle 2, all the way to the pressure due to particle n. So what is the average pressure due to particle 1? That's going to be m times v1x squared over v plus m v2x squared over v plus dot 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 plus m v n x squared over v. And as you can see, the mass and the volume are constant, which means we can factorize them out. And then we're left with v1x squared plus v2x squared. And this goes all the way to vnx squared. There we go. This is the sum of squares. Wow. Further maths, flashback. Never mind, we're not going to do that. Okay, so let's move on to F. In order to simplify this a bit further, we're going to use the mean squared speed. All this is in your syllabus, by the way. All these steps here, this is all in your syllabus for physics, so you need to make sure that you understand each of these steps. So in the actual exam, they're not going to ask you to derive the whole thing, but they would ask you to derive parts of it. It could be maybe this two, it could be maybe this two, it could be the first three, you never know. So you need to familiarize yourself with the entire process and know what's going on. Anyway, we're going to use this expression here for the mean squared speed. So what does the mean squared speed tell you? Well, the mean squared speed is essentially adding up all these square terms here. So you take the square of the first particle, the speed of the first particle, add it with the square of the other particles and add it up. So that's the sum of the squares. And then you divide that by the number of particles, capital N, which is going to give you the mean of the sum of the squares. So usually they refer to this as the mean squared speed, which is essentially the mean of the sum of the squares. Okay? And it's written in summation notation like that. If you haven't done further math, you probably don't recognize this. But what this essentially tells you is you're adding up all the squares and you divide by the number of particles. So this plus this plus this plus this all the way to the n, divide by n. That's this guy here. Okay? So if we rearrange this, you'll see that n times the mean square speed is actually equals to the sum of I equals 1 to n of vix squared, which is actually v1x squared plus v2x squared plus all the way to v capital N x squared. Okay. Right, so moving on, you can see that this guy here is actually this guy. And you can see this guy here is actually this guy. So we can actually replace this whole thing with this guy, which is much neater. So that's what we're going to do. So the total pressure, or the pressure of n particles, is going to be m over v times n times the mean squared speed. There we go. So we have gotten this so far. And as you can see, or as you can probably tell, we are getting closer and closer to our final objective, which is the equation of state of the ideal gas. PV equals nRT. Okay? All right. So, however, in an actual gas, in an actual ideal gas, all the particles will not just be moving in the x direction. They will be moving in a random direction. It could be moving in the y direction, the z direction, maybe a bit of y, a bit of z, a bit of x, a bit of y. It's random, right? There is no preference for a particular direction. But the equation that we've gotten so far is only for the x direction, which is, not representative of the actual gas. So how do we correct that? Well, assuming that the gas moves in a completely random fashion and there is no preference for a particular direction, if we have a large number of gas particles, we can make an assumption that the particles are moving in all directions and with equal probability. So maybe 33% is moving in the x direction, 33% in the y direction, 33% in the z direction, and it's sort of split up like so. Okay? So what we could say is that the average of the x direction plus the average of the y direction plus the average of the z direction, and then we add them out all up and we square root that, we are going to get the average velocity of the average speed of the particle. So say you have a particle moving in some random direction, and this random direction has a component in the x, y, and z direction. So how do you find the speed of this particle? You have to do a triple Pythagorean theorem thing, right? So when you do a Pythagorean theorem thing for a two-dimensional object, let's say you want to find the speed, and then you have Vx and Vy. You have to do Vx squared plus Vy squared, and then you square root, and then you get V, right? But if you have an object in 3 dimensions, you have to do that for x, y, and z. That's why you're doing it 3 times. So you see here, this is actually a triple Pythagorean theorem thingy that we are doing. So by doing a triple Pythagorean theorem thingy, we are going to get our mean speed in 3-dimensional space. And we're going to make the assumption that Vx, Vy, and Vz are the same. So the average is the same, because one of the assumptions for the ideal gas is that it's moving in a random direction. There is no special preference in a particular direction, which means the average speed of the particles, if you sum up all the particles and you take the average speed, the averages would be the same in all directions, right? So we can say that this must be the same as this, and this must be the same as this. Therefore, we can actually rewrite this equation here into V is equals to 3 times of this, and then square root, which means the square of this must be equals to 3 Vx square, which means Vx square must be equals to 1/3 of V squared. Now we're getting somewhere, because look at this guy here. We have the total pressure is this times this times this, but this guy is actually this guy, which is this guy. Haha! So therefore, we can write Pn is equals to m over v times n times 1 over 3 times the root mean square speed. So this one here is the root mean square speed in the x direction. This one is the root mean square speed in all directions. So now we are done. Okay, excellent. Right. So what are we gonna do next? Let's see. Let me just rewrite this a bit neatly. So that's gonna give me 1 over 3 times mn over v times v root mean square speed. There we go. Okay, so next up, we're gonna rewrite this constant here in terms of the number of moles. So the number of moles of a gas is actually the total number of particles of the gas, capital N, divided by the Avogadro number. Okay, and the molar gas constant R is related to the Avogadro number via this equation here. So it's the product of the Boltzmann constant, which is again just a different constant, times the Avogadro number. So, we have Pn equals to 1 over 3 m over v, capital V, small v squared, and then capital N, right? But its capital N is actually n times Na from this guy here. And you can see from this guy, Na is in fact R over Kb. Okay, so actually let me think. Do I want to write it like this? Oh wait, hang on. That's not what we're trying to do here. Hang on a second. Yeah. So going back to our ideal gas equation, the one that we derive experimentally from scratch, we know that PV is equals to nRT, right? This is derived experimentally using the three gas laws. So now we're going to try to rewrite the number of moles in terms of capital N and Kb. So that's going to give me N over Na, and then Na is going to be R over Kb. So let's see. So the R's would cancel, which means we're left with NKBT. So this is the alternate form of the ideal gas equation. So on one hand, we have PV equals nRT. On the other hand, we have PV equals to capital N KBT. So this is another thing that you have to know as well. The only difference here is that this big N here refers to the number of particles instead of the number of moles. And this Kb is the Boltzmann constant right there. Okay, so depending on whether they've given you the number of particles or the number of moles, you have to use one of these equations. It's a bit like when we did centripetal force. Sometimes you use m omega squared r, sometimes you use mv squared over r. Depends on what values the question has given you. Okay, so now we're gonna move on to this guy here. Okay, so if we derive it using the ideal gas assumptions, and using a bit of math, we actually get this equation here. But this is the equation that we get when we derive it experimentally, right? So just to show you something, from this equation, we can actually get PV equals to 1 over 3 mn v squared. Okay, I've just moved the volume up here. So this pressure refers to the pressure of the gas, which is the same as this value here. V is the volume of volume occupied by the gas, which is the same as the volume of the container. So the V's are actually referring to the same value. And therefore, this guy here on the right must be equals to this guy here on the right. You see that? Which means we can write 1 over 3 m and v squared must be equals to nkbt. Now this is what we are trying to do, because now we can show that the, okay, you know what, let me just work this out and then you see what I mean. We'll get rid of the capital N first. Bye-bye. Okay, and then wait, let me think. No, we don't get rid of the capital N. Yep. So N here refers to the number of particles. Actually, yeah, let's get rid of the N. Let's get rid of the N because they are the same on both sides. Okay, and then we're going to try to make the left side look like the term for kinetic energy. So the kinetic energy is half mv squared, right? But here we have a third mv squared. So we're going to multiply the left side by 2 over 2. And then we're going to swap the order for the denominators. So we have 2 over 3 and then 1 over 2. And then we're going to move the 2 over 3 to the other side. Okay, so as you can see here on the left, we have half mv squared. So what does the half mv squared mean? The half mv squared here actually refers to the mean translational kinetic energy of the gas. The m here actually refers to the mass of one particle of the gas. So if you're trying to refer to the mean translation energy of all the gas particles, you have to multiply both sides by n. So you can multiply, so this actually refers to the total mass of gas particles. But this m here is just the mass of one particle. So if you multiply this by n, that means this guy on the right would be nkbt. There we go. So this guy here on the left, this entire thing here is the mean translational kinetic energy of the gas. So that's going to be EK with the mean notation equals to 3 over 2 nkbt. And this is what we are trying to do using all of that, aside from deriving the equation of state of the gas. We also want to show that the temperature depends only on the mean translational kinetic energy of the gas. So you can see here that N and Kb are just constants. 3 over 2 is a constant. So therefore, the temperature of an ideal gas is proportional to the mean translational kinetic energy of the gas particles. Why do I say translational? Because translational here means it's moving left, right, up, down, forwards, backwards. That's what translation means. You're just displacing the particle. So the kinetic energy here is only associated with the movement of the particle in 3D space. But it has nothing to do with the vibrational energy or rotational energy, which is present in some of the more complex non-ideal gases. So, but for a For an ideal gas, the temperature only depends on the translational kinetic energy of the gas, the mean translational kinetic energy of the gas. Okay, so this is what you want to take away from doing all of this. So now we have actually found what the temperature of an ideal gas actually means. It just tells you a measure of the mean translational kinetic energy of the gas. It is something that is measurable. Okay, so using the temperature derived above, which is this relationship here, suggests what is meant by the absolute zero of the temperature of the gas, of an ideal gas. So if you have an ideal gas and it is at absolute zero, let me say that it is at 0 kelvins, what does that actually tell you? It tells you that the mean translational kinetic energy of the gas must be 0, or it is the minimum energy of the gas. Okay, so it tells you that if T is 0 kelvins, then the mean translational kinetic energy is going to be 0 as well. So this is the minimum energy state of an ideal gas. There we go. Okay. Right, so far we have come across 3 equations. The first equation is this one, Ek equals to 3 over 2 nkBT. The second equation is this one, PV equals to nkBT. And the last equation is PV equals nRT. So far we know 3 equations. And this one is also helpful to know, but not really necessary. There we go. Okay, so next up we're going to derive the fourth equation, which is this guy here. The pressure is equals to 1 over 3 rho V squared. So this one actually comes from this guy here, 3 over 2 kBT. And we're going to equate that with the mean translational kinetic energy, which is half mv squared. So we're just going backwards a bit. So going from here, going back to here. Okay, this m here refers to the mass of one particle, not the mass of the whole gaseous particles. It's just one particle, okay? And you want to make T the subject, so you get something like that. And then you want to substitute that into PV equals to nkBT, which is this guy right here. So you substitute that in here, and you would get this guy. Rearranging this, you would get this. And you can see that Nm here refers to the total mass of the gas, and V here refers to the volume of the gas. So total mass divided by volume is the density of the gas. That's how you get this guy. So this derivation is actually very important. You should try to do this from scratch because they've actually asked this on several occasions in paper 4. So try to work this out from scratch if you can and see whether you can get this expression right here. Okay, so we have done 4 equations. Cool. All right, so that's it, really. So we're done with ideal gases. We have a bunch of thingy right here. You know what? Let's do one question. We'll do one question and then we will continue with the rest another time. Okay, so far gravitational forces have been neglected. We will now attempt to justify that. Right? Because if you remember, one of the ideal gas assumptions is we ignore gravitational forces. So assuming air is made up of nitrogen molecules, calculate the energy required for the nitrogen molecule to be lifted 1 meter from the surface of the Earth. Okay, so how much energy do you need to lift a nitrogen molecule 1 meter from the surface of the Earth? So assuming that the gravitational acceleration is constant, which is a fair approximation to make since you are lifting it only 1 meter above the surface of the Earth, we can just use mgh. So the energy required is going to be mgh. M is going to be the mass of a nitrogen molecule, which is 28 atomic mass unit. So 28 times 1.66 times 10 to the power of negative 27 kilograms. G is 9.81. H is 1 meter. So what am I going to get? Calculator. So we're going to end up with 4.56 times 10 to the power of negative 25 joules. All right, cool. What is the mean kinetic energy of the molecule at a room temperature of 25 degrees Celsius? So how do I find the mean kinetic energy of a molecule? So this is a nitrogen molecule. We're going to assume that it is an ideal gas, okay? And if we assume it's an ideal gas, we can use the equation that the mean kinetic energy is actually 3/2 kBT. So kB, the Boltzmann constant, is 1.38 times 10 to the power of negative 23. T is the absolute temperature, which is going to be 25 plus 273. Remember, you have to convert the temperature to kelvins before you do this. So 25 plus 273 times 3/2 times 1.38 times 10 to the power of negative 23, which is going to give us 6.17 times 10 to the power of negative 21 joules. As you can see, if you compare the kinetic energy to the potential energy, the kinetic energy is about 10,000 times more than the potential energy. Okay, so compare and comment on the two values obtained with reference to one of the assumptions of the kinetic theory of gases. So the mean kinetic energy of the gas is about 10,000 times greater than the potential energy required to lift it by 1 meter. Okay, so the atmosphere is held in place by the gravitational forces of the Earth. Wait, I'm not done with this because we have to refer to one of the assumptions of the kinetic theory of gases. So what does this mean? So this justifies the assumption that gravitational forces can be neglected. Okay? If this is not obvious as to why we can ignore gravitational forces, think about it this way. Usually when we increase the height of an object, or when we lift something up, or let's say we throw a ball, right? We throw a ball and the ball flies into the air. What's actually happening there? The gravitational potential energy is increasing, but the kinetic energy is decreasing, right? So we have to account for gravitational forces in that scenario because the increase in the gravitational potential energy is significant, which causes a significant decrease in the kinetic energy. However, when you look at this guy here, when you throw the nitrogen molecule 1 meter into the air, it only decreases it by a factor of 1/10,000. So the decrease in the kinetic energy is insignificant, which means we can just ignore any decrease in the kinetic energy due to an increase in potential energy, because it is so tiny that we can just ignore it, if that makes sense, right? Which justifies the assumption that we can ignore gravitational forces when it comes to ideal gases. So one interesting calculation that you can do here is trying to estimate the thickness of the atmosphere of the Earth. assuming, of course, that the atmosphere is made entirely of nitrogen, which is not the most accurate approximation, but the atmosphere is 78% nitrogen, so it's a fair approximation. Okay, so suppose this nitrogen molecule flies up into the air vertically until a point where it stops. So that's going to be the upper limit of our atmosphere, right? So let's try to do that. Change in kinetic energy equals to negative the change in potential energy. This is from the master equation. So let's say we have a nitrogen molecule on the surface of the Earth, and it flies up into the air, and it stops at some point here. So we say V0 up here. Okay, so my final kinetic energy is half m0 squared. Initial kinetic energy is going to be half m. So what is my initial speed going to be? The initial kinetic energy. Well, we know it's actually this guy here, 6.17 times 10 to the negative 21. So we can actually just replace this guy here with 6.17 times 10 to the negative 21. Okay, what about my final, what about the change in gravitational potential energy? So since you're flying all the way into the atmosphere, that's going to be way more than 1 meter. And I suspect the gravitational force would not be constant anymore, right? Because from chapter 2, you know that the gravitational acceleration depends on the distance to the center of the Earth. So we have to use the gravitational potential energy equation, which is negative gmm over r. Okay, so final is negative gmm over rf minus positive gmm over ri. So we're gonna factorize gmm, so that's gonna give us gmm 1 over rf minus 1 over ri. Okay. So G is going to be 6.67. You know what? Let me just simplify this a bit. Get rid of that. Let me just leave that as G for now. So GMM. So what is the final distance from the center of the Earth? Well, the final distance is going to be the radius of the Earth, which is 6.37 times 10 to the power 6. Or you know what? I'll just leave it as RE for now. Resident Evil. Haha. Plus the altitude. So that's going to be H. So RE is like this. And then H is like that. Okay. And then RI is just RE. There we go. Okay. And yep. Right. This is going to be quite messy. Let me see. How can I simplify this further? So we actually have all these unknowns already. We know what the G is, we know what the mass of the Earth is, we know what the mass of a single molecule of nitrogen 28 is. We know what the radius of the Earth is, so we can actually work out H. This is going to be a pain though, because you're going to get a quadratic, I think. Okay, you know what? Let me try to simplify by moving the GMM over to the other side first. So we have negative 6.17 times 10 to the power of negative 21. I'm going to divide that by G, which is 6.67 times 10 to the power of negative 11. And then we're going to divide that by the mass of the Earth, which is 5.97 times 10 to the power 24. And then we're going to divide that by the mass of a nitrogen molecule, which is 28 times the atomic mass unit, which is 1.66 times 10 to the power negative 27. And that's going to end up with negative 3.33 times 10 to the power negative 10 equals to 1 over Re plus H minus 1 over Re. Okay, I'm going to move 1 over Re over, so that's going to be plus 1 over the radius of the Earth, which is 6.37 times 10 to the power 6, which is going to give us 1.57 times 10 to the power of negative 7 equals to 1 over Re plus H. So Re plus H is equals to 1 over 1.57 times 10 to the power negative 7, which is 1, 2, 3, 4, 5, 6. So 6.38 times 10 to the power 6 meters. Therefore, H is going to be that guy minus the radius of the Earth, which is 6.37 times 10 to the power 6, which gives us 13556 meters, which is roughly 13.6 kilometers. So according to this very rough calculation that we've made, the atmosphere of the Earth is about 13.6 kilometers. So let's see if that is actually the case. So this is the diagram that I got from Wikipedia. And as you can see, the troposphere, which holds most of our atmosphere, is about 15 kilometers. So yeah, that is pretty accurate. We got pretty close to the actual value. The power of math. Okay, there we go. So that's how you estimate the thickness of the atmosphere. All right, so we're gonna do the rest of this in our next class, which I believe is Friday. So I'll see you guys then. Until then, goodbye. And yep, bye-bye.